Everyone, the screen is visible, right?
Yes, sir.
Yeah. Okay. So good afternoon all. Welcome all to the live session 2. So just like the previous session, today also you will work on few simple problems which may help you to solve this week's assignment. So let's start straight away. The question 1, it tells about, let us assume a 1D heat transfer problem where two boundaries of a plane are at a temperature of 150 degree. The thickness of the plane is 10 mm. Assume the convection and radiation is negligible. It is given that net heat accumulated in the system is 500 watt. So what will be the conductivity of the material?
Sorry, your screen isn't visible.
It's
Sorry,
not.
screen is not visible.
Yes, sir.
Is it visible now?
Yes, sir.
Okay. Can you work on the first problem? It's basically, I have improvised the governing equation a little bit, but the concept is a little, means it is same, the concept. So it's basically the heat transfer problem. In general, what you see in the heat transfer equation is basically like this. Is it not? So this is heat due to conduction. So in real system, of course, your heat flux will vary with position and time. So you can write it like this, and this is your constitutive material law, right? dTdx. This is your Fourier's heat law of conduction. So in this question, you can assume this thing as a constant term. Means it is not varying with time and it is not varying in space. So basically, what is the net heat entering into the system? It is governing by the this equation only. Qx equal to Ka dt dx. Total surface heat flux. And what is this? Can anyone tell me? What is Cp?
Heat, sir.
Sorry.
Specific heat.
Can you get louder?
Specific heat at constant pressure.
Right. So Cp is basically what Cp basically tells about. It is the property of how much energy can get stored, right? So depending on your Cp value, that net heat accumulation will depend upon. So this value is given as something like 500 watt, and you can assume there is no heat generation. So you can simplify the problem like this. It's basically Ka dt dx equal to 500. Is it not? Am I right?
Yes, sir.
So what is your surface area? This is something like 15 to 100. This one, right? And your dt temperature gradient is 100 minus 50 divided by 50. The thickness is of 50 mm equal to 500. From here, can you calculate the K? Can you give me an answer?
Zero point 0.1.
Okay, I don't know the answer. Maybe it's too low. Basically, this is the equation what you need to. Let me clear up the things. But you got K equal to 0.1, right? I'm taking it as correct value. Sorry. Okay, let's go to the next question. Uh, you got the concept right for question 1.
Yes, sir. Yes, sir.
So in question 2, it tells about a cylindrical test specimen of diameter 10 mm and gauge length of 50 mm is extended to L equal to 65 mm. So here is your cylindrical test specimen, which is having a length of 50 mm and the extension is 15 mm. So the total length has been up to L equal to 65 mm. Determine the true strain. If ultimate strength occur at a force of 25,000 Newton and at an extension of L equal to 70 mm, determine the strain hardening exponent and ultimate strength of the material. You need to calculate N. Assume that your stress strain value is following this power law hardening law, and what will be the ultimate strength? Can you tell me what will be the what will be the true strain value at the point of UTS? Give me a quick number. What is L2 here?
70.
So at the point of ultimate strength, this is extended up to L equal to 70 mm, and the initial length was 50 mm. How much is this?
0.336.
0.336. Okay. So can you somehow relate this strain value to the strain hardening exponent, or how would you calculate this n value? Are you familiar with this relation? Are you familiar with this relation? Yes or no? Okay, let me explain why it is coming like that. Uh, so what force can be written as F equal to sigma into A, right? So if you differentiate F, right? Now what will be the dF by F? Okay. Now tell that at the point of UTS, dF by F equal to 0. Why? Because the loading is constant. The load value which you are applying is constant throughout. Its differentiation is 0. So, right? Now During plastic deformation, is my screen visible?
Yes,
Yes.
sir.
Now during plastic deformation, your volume remains constant. So dV is 0. Sorry guys. So the area into length is basically 0. So from here you can get this relation. Is it clear up to this point?
Yes.
Area into length will be equal to constant. So
Sorry.
A into L is equal to constant. So
Area into length. So your volume is basically area, the cross sectional area and the length. That remains constant.
but A is equal to 0.
Is it okay
Yes,
now?
okay, sir.
The
Thank you, sir.
differentiation of
Yes,
area
thank
into
you, sir.
length. Okay. So here you have two equations. So d sigma by sigma is basically coming as dl by l. What is this? Is this your strain? The engineering strain. So finally you end up with this equation. Basically at the point of necking, or when the spaceman is taking the maximum amount of load, this relation dictates that whether the necking has been happened or it's still going to occur. So if you assume this relation, so this is your say 3, this is your 4. Now can you give me a relation between n and epsilon? Sorry. Is it okay until this?
Yes, sir.
Yes, yes.
So you got your strain value at the point of UTS is as 0.336. So simply at the point of UTS, N also will be 0.336. What will be the ultimate strength of the material? Say this is L2 by L1. Can you relate it to area somehow? Tell me, is this right or wrong?
Right, sir.
Mm-hmm. It's basically volume preserving, right? A1 L1 equal to A2 L2. Simple. So, yeah. What was your initial cross-sectional area? It was pi d square by 4. So, it was 0.336, right? 0.336 equal to, right? Can you give me a number for D? So, D is the diameter at the point of ultimate tensile strength. How much is D?
Sir, I think it's 8.45 millimeters.
8.45, right?
Yes, sir.
Yeah. Okay. So, simply sigma ultimate will be what? It is taking load of 25,000 Newton pi into T square by 4 megapascal. How much it is?
For 45.4 MPa.
Sorry,
445.4.
445. 445. Okay, concepts are clear for question 2. So the trick was basically here. At the point of necking or whenever the specimen is taking the maximum amount of load, always uh, the value of strain where it reaches, it will be equal to the strain hardening exponent. So let's jump to question 3. Tells that K is your 1140, sorry, strain visible, right?
Yes, yes.
Yeah. N is 0.35 and is 0.01. So you can assume that this is a strain rate dependent stress behavior. So it tells about it has a length of 50 mm, thickness is of 0.45 mm. These are some arbitrary values I have kept here. Width is something 12.5 mm, and it tells that you need to determine the increase in load when extension is 10%. So you calculate the strain. How much is strain? There is an 10% extension. Am I right?
Yeah.
So how much is the strain? Give me a quick number.
0.095.
0.095, right?
Yes.
Okay. So now it tells that up to this point is okay. Now it tells that your when you are extending the sample up to 10% during that time, say one is your case 1, when your gauge length changes to rate of 0.5 mm per minute, and your case 2 is 50 mm per minute. Which one will give you the higher stress value? How does stress depend upon the strain rate when it is different loading rate? There is two cases. Which one will give you the higher stress value?
Please scroll up. It's not visible at that corner.
Sorry, what should I do?
Please scroll up.
Case 2, right? So one is your 50 mm per minute, one is your 0.5 mm per minute. So wherever the loading rate is higher, your strain rate is higher, so your stress value will be higher. Sigma for case 2 will be higher than sigma 1. Now from this equation, you calculate what is sigma 1 and what is sigma 2. There are two different cases of epsilon dot. You have the n and m values. You got my point? Hmm? Okay, epsilon to the power 0.35 into how much? 0.5 to the power 0.01.
496.70.
Is this the final answer?
That's the sigma 1.
Sigma 1. 496? Okay, 496.
496.70.
496.70.
Sigma 2 is 570.12, sir.
570.
0.12.
Yeah. So you need to calculate the area to get the force value. The instantaneous area, right? When the extension has been happened. These are your original, the initial. How much will be the area? How much it is? 12.5 into 0.45 into 50. 50 plus 1 into 50. Can you calculate?
A0 into L0 will be there.
Sorry.
A0 into L0 is there. So you need to multiply 50 times more in the numerator.
A0 is your this cross sectional area.
Oh, sorry. Okay.
How much it is?
5.11.
Okay, 5.1. So you got your del F. It's 5.11 into sigma 1 minus sigma 2. Okay. Okay, you can calculate it later also. Got the concept, right? Should I move
Yeah.
to the next question? Should I?
The del F will be 375.07.
Sorry, which one?
Del F.
Del F is 375.07.
Yeah, there will be negative sign also there.
Okay. Negative. Yeah, means the increase in load is basically the magnitude part.
Yeah.
Yeah.
Good. Sorry.
So this was the concept I was talking about, that d sigma by d epsilon will be sigma at the point of necking. So I have taken the same values for K and N here. K is 1140 megapascal, N is 0.35. The strain value is determined as 0.38 at a certain point of loading. So at certain point of loading, you have the strain as 0.38. Your UTS is given as 515. So the question asks that has the material started to neck or not? If it is less than UTS, Now tell me the answer. Sigma is k epsilon to the power n. How much is this value? D sigma by d epsilon.
212.73, sir.
212 roughly, right?
Yes.
So your UTS is 515. So it has not started today. Okay.
Actually, I am getting 748.36.
Yes, sir. Even I'm getting 748.
748.
Yeah, 748.36.
Okay. There are two answers. Then let me bring my calculator. Wait. Minus 0.65. 324 minus 0.65 into 0.35. Yeah, this is coming at 748.36. So whoever got the answer of 212, please check once.
Yes, sir. I've neglected the negative sign in the power.
Okay,
I got it.
okay, okay. So let's move to the next question. What does it tell? For an engineering material, the true stress value is 1000. If engineering strain value, so I will notify like this way: S and E for engineering stress strain, sigma and epsilon for true stress strain for this problem. Okay. So your engineering strain is given as 0.25. K is given as 500 megapascal. What is value of N and what is value of S? So it's basically relating true stress strain to engineering stress strain and vice versa. So you can assume this true stress value, whatever is given as the UTS for this problem. I forgot to mention, otherwise you can't relate this equation. So you first calculate the true strain value. What is the true strain? So whenever you get the true strain, you can equate it to the strain hardening exponent.
Point 223.
0.223. 0.223. Then your n value is 0.223. What is the engineering stress? Tell me if you don't understand any of these derivations. These are very simple. So it very meshy. Just wait.
800.
Anyone else who got the answer? Okay, let's take it as correct. Let's move to the next question. So you have given a biaxial stress rate. You need to find out max and mean principal stresses and the plane of it, the max shear stress and the plane of it. I think you are familiar with this from solid mechanics classes. These are not very difficult things, right? I'm writing the equation once again. You just give me a number, please. Correct me if the equations are wrong. So this is your max and mean principal stresses.
Maximum principal stress will be 50 and minimum is 0. Sigma 1 is 50 and sigma 2 is 0.
Zero. Oh, okay.
Yeah, it's coming out like that.
Any other please confirm this answer?
Maximum shear stress is 25.
These things you can get from more circles also.
Yeah.
This was a very simple problem. Okay, let's leave it here. Others, can you please confirm this answer? 25, 50, and 0. And you can calculate the theta s and theta p also. Should I move to the next question?
Yes, yes, please.
Sir,
How many questions are there? 10.
There, I have given 9 questions.
Okay.
So it is a 3D stress state. You need to find out what will be the hydrostatic part of the stress state and the state which will cause the plastic deformation. You are familiar with this equation? Mm-hmm. So in your system, it can be decomposed into two different parts. So one part which will cause only means which will cause the volume change of the system, and another part which does not cause the plastic deformation thing. So this is simply a pressure term. I should write it as hydrostatic pressure. Hydrostatic pressure does not cause the plastic deformation. It is calculated as the principal's average of this principal stresses. How much is this? 68 by 3, right?
Yes.
68 by 3. This is coming as something like this. So if you get the hydrostatic part of the stress state, so there should be some part which will cause the deformation. So the shear parts will
So the
change.
hydrostatic state,
Mm-hmm.
hello,
Mm-hmm.
the hydrostatic stress only cause the elastic volume change.
Right,
Yeah.
right.
Okay.
The shear components will not affected by the hydrostatic part. So this is the actual stress state which will cause your plastic deformation. How much will be this? Okay, you can calculate this 40 minus 22, 10, 5. This will remain same. The shear parts will remain same. These all will remain same. You just subtract the hydrostatic part from the actual stress state, right?
Yes.
Let's move to next question. All okay for everyone? Okay. Let's move to next question. You need to find out the strain ratio for a condition. So the condition is uniaxial tension where sigma 1 is given as sigma and the other two parts are 0. So you can refer this flow rule and normality condition.
Yeah, it will be 2 is to minus 1 is to minus 1, right?
So this as per this flow rules and normality condition, what does it tell? It basically tells that how should I convey? Yeah, in any plastic deformation process, the work done will be positive, and the strain increment vector is always normal to the yield surface. So what will be the work done? Work done will be, it's simply the sigma into epsilon, right? So as per the flow rules, it tells that work done will always be positive, and it's also tell that the strain increment is directly proportional to corresponding deviatory part of the stress component. So simply tells like this: del this is your actual relation of plastic stress and plastic strain as per this flow rule.
Yes.
I'm trying to explain why it is coming as 2 is to minus 1 is to minus 1, or how is it coming. So what is your f? F is basically your yield function, right? So as per von Mises, what will be your f? It is something like this. Can you find out what will be the strain increment at x1 direction? By differentiating this function with respect to sigma 1.
It will be 2 sigma 1 minus sigma 2 minus sigma 3 into d lambda.
Correct. So similarly, you will get d epsilon 2 and d epsilon 3.
And then I have to put the values of sigma 1,
Right.
sigma 2, and sigma.
Okay. Okay. This is my last question. Tells about you have a rod of length 0.5 mm, sorry, 0.5 meter. Should I do it as 0.5 meter or mm? Let us make it mm because I have given E value in terms
We
of
have
megapascal.
megapixel. Yes.
0.5 mm. So it tells that from 20 degree to 80 degree. While what happened? Someone wants to join now. Screen visible, right? Is my screen visible?
No.
No.
Yes, sir. Yes, sir. Right now it is visible.
Yes.
Yes, yes.
Okay. It tells that at one end it is fixed. Assume that initially it was at 20 degree C, then it is heated to 80 degree C. This is your case 1. What will be the nature and value of stress? It will be basically a thermal stress or residual stress, however you want to call it. This was 20 degree C minus 10 degree C. It will be the nature and magnitude. So for the case 1, the rod will shrink or expand. Let's understand it physically first. Otherwise, you have the equation, of course. It will shrink or expand if it is heating up. Sorry,
हाँ ले जाओ. No, please continue.
it will try to expand. So if it is trying to expand, the end of the system will experience a tensile kind of thing. So if you see in the inner part, to balance that, you'll get a compressive residual stress when the material is getting heated up. So what is sigma thermal? Right?
Yeah.
207 into 10 cube into alpha. What is your del T? Minus 60. So this will be something. Can you give me a answer? And it will be compressive in nature.
145.314.
Now for the case 2, you are cooling the system from 20 degree to minus 10. So it will try to shrink up. So at the boundary, it will experience a compressive stress. But if you see the inner part, to balance that, you'll get a tensile kind of stress. Twenty minus 10, yeah.
72. Yeah,
72.
72.65.
Yeah. So this is compressive, this is tensile. Okay.
Okay.
That's it
Can
from
we
my side. Yeah.
upload these questions in?
Yes, yes.
Can we upload
Actually,
these questions?
I'm uploading these things to NPTEL team. Maybe they will share the things with you guys. So I'm not
Okay.
directly relating it with you.
Yeah, yeah.
Yeah.
Uh,
So this will be there. Don't worry.
okay.
Okay.
Okay. Thank you. And you are a PhD scholar in which year? May I know?
This is my 1.5 year now.
Oh,
IIT KGP.
IIT KGP. But sir is from the IIT Guwahati, na?
Yeah, sir is from IIT Guwahati. Actually, we are actually a PMRF scholar. So
Oh,
this is kind of something you call it deliverables or whatever. So we have given a task to give some live session with you guys.
oh. Actually, I thought the scholars which is under the
Ha 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 ha.
Saurabh Bagh, sir,
Ha ha ha.
he used to take. Okay, no problem. Thank you.
Yeah. Thank you. Have a good day.
Thank you so much,
Same
sir.
to you.